Hello students, in today's lecture I will discuss about composite transformation. So before dealing with composite transformation we have to see what is homogeneous coordinates. What is happening? We have already seen 5 transformations: translation, rotation, scaling, reflection and shear. So what we are doing, we are representing all those transformations as homogeneous matrix. Okay, so for that we have to study homogeneous coordinates. A point x comma y can be rewritten in homogeneous coordinates as xh comma yh comma h. So we are dealing with a two-dimensional transformation, and in two-dimensional transformation we are having x coordinate and y coordinate. Now what we are doing, we are representing this coordinate as homogeneous coordinate, and for that the homogeneous parameter h is a non-zero value such that x is equals to xh upon h and y is equals to yh upon h. So we are adding one more factor or parameter that we are calling as homogeneous parameter, and we can see that this parameter could be defined in this way. Now we can write any point x comma y as hx comma hy comma h. So if you are substituting the value of xh as hx, yh as hy, and h will remain same, then obviously we can see that the point x comma y will become hx comma hy comma h. Now we are keeping the value of h as 1, so finally we will get it as x comma y comma 1. So the question arises, why we are representing any point x comma y as a homogeneous? So you have already seen that whenever you are dealing with transformations, in translation we are adding the values, while in case of rotation and scaling we are doing the multiplication. So in translation we are adding the values, in rotation and scaling we are using the multiplication. So using homogeneous coordinates allows us use matrix multiplication to calculate transformations extremely efficient. So what is happening? We are performing a kind of composite transformations. We are performing more than one transformation. So better is that we should stick on one calculation. Previously we are doing addition as well as we are doing multiplication, but as you are representing the matrices as homogeneous form, so in that case you have to perform one operation, and the one operation is what? It is a kind of multiplication. Each and every transformation, whether it is translation, whether it is rotation, or whether it is scaling, it can be performed with a single calculation, and the calculation is multiplication. Each matrix is represented as 3 by 3 matrices. And one thing in this we have to keep in our mind, whenever you are representing any matrix by using homogeneous coordinate representation, all matrices will be of order 3 by 3 and you have to perform multiplication. So you can see that in translation what we are doing, we are changing the position of an object, and the translation vectors are dx and dy. So this transformation can be represented in homogeneous matrix form as 1 0 dx, 0 1 dy and 0 0 1. And you can easily see that in translation we are doing the addition. So it is a kind of adding the values or adding the translation vector, and we have already seen that whenever you are adding the translation vector, the new coordinate will be x dash is equals to x plus dx, and y dash is equals to y plus dy. So if you are representing the matrices, if you are representing the transformation, that is a translation in this form, so it is giving you x plus dx and y plus dy. Similarly, we can represent other transformation like scaling as sx00, 0 sy0, and 001. So this is the way to represent translation, and this is the way to represent scaling. Now rotation we have already seen the equations. It is written as cos theta minus sin theta cos theta. So in this we are representing it as a 3 by 3 matrix, so it becomes cos theta minus sin theta 0, sin theta cos theta 0, 0 0 1. And whenever you are solving this equation, the exact coordinate will become x cos theta minus y sin theta, and y dash coordinate will become x sin theta plus y cos theta. So whenever you are applying the transformations, or whenever you are using these three matrices, whether I speak about translation, whether I speak about scaling, or whether I speak about rotation, whenever you are applying all these three matrices, these all three transformations give a translation, rotation, and scaling about origin. So whenever you are applying all these three transformations, they are translating, they are rotating, and they are scaling the object about origin. So whenever there is a question about transformation about origin, you can directly apply these three matrices. But if I am saying that you have to translate the object about any pivot point or any fixed point, in that case you have to apply some different matrices that we will discuss in the coming section. Now we have already seen how to represent any matrix in homogeneous form. Now after representing the matrices in homogeneous form, we can able to perform composite transformation. Composite transformation is nothing but it is a kind of performing more than one transformation. So whenever you are doing more than one transformation, then it is a kind of composite transformation. That means it is combining more than one transformation. Performing more than one transformation is called as composite transformation. So whether you are rotating any object about pivot point, you are scaling about any object about a fixed point, or you are doing reflection about y is equals to mx plus b, or you are performing more than one transformation, like two translation, like two scaling or rotation. So all these things are what they are, a kind of composite transformations. So we will start from rotation about pivot point. We have already seen how to rotate an object about origin. If you are rotating an object about origin, then you can directly apply this matrix. Okay, but if the question is like you have to rotate an object about pivot point, in that case you have to perform more than one transformation. So rotation about pivot point, this involves three operations. First is we have to perform translation to center point to origin. Then we have to perform rotation, and we have to perform translation back to the center point. So you can see in the figure here I am having an object H, and I have to perform rotation of this object about pivot point. So in the first step, what I am doing, I am translating this object at the origin. As the object comes at origin, I know the rotation matrix about origin, so I am applying the rotation, and after applying the operation rotation, I am translating this object back to its original position. So you can see that in this I am performing translation. In the second step I am performing translation. In the third step I am performing rotation, and in the fourth step I am performing reverse translation. So this transformation can be written as translation minus dx comma minus dy into rotation with an angle theta into translation again with the value dx comma dy. And one thing you have to keep in your mind, whenever you are moving an object towards origin, you have to keep the values as negative, and whenever you are shifting the object away from origin, you have to keep the value as positive. So you have to multiply all these three matrices, then you will get rotation about pivot point. So you can see that I am multiplying three matrices. First matrix is the translation matrix, second matrix is the rotation matrix, and third matrix is the translation matrix. And after multiplying all these three matrices, I will get the composite transformation. And finally what is happening, I have to multiply all these matrices with the object matrix. For example, if the object is point, I will write the matrix as xy1. If the object is a line, I will write the matrix as x1 y1 1, x2 y2 1. If the object is triangle, I will write it as x1 y1 1, x2 y2 1, x3 y3 1. So we are representing the object matrix as a column vector. Okay, and you should keep one thing in your mind, the matrix multiplication is not commutative, so the order of matrices is very important. That means A into B is not same as that of B into A. Now composition of two translations. Now in this we are performing two translation. For example, if I am having a point, so I am translating the point twice. Let T1, T2, T3 and T4 are translation vectors. They are two translations P1 and P2. The matrix of P1 and P2 is given below. The P1 and P2 are represented using homogeneous matrices, and P will be the final transformation matrix obtained after multiplication. So initially we are translating the object with the value T1 and T2, and in the second time what we are doing, we are translating the object with the value T3 and T4. So two successive translations are nothing but they are a kind of addition. So the resultant matrix will be 1 0 T1 plus T3, 0 1 T2 plus T4, 0 0 1. So we can see that above resultant matrix shows that two successive translations are additive. Similarly, two successive rotations are also additive. For example, if you are rotating an object with an angle 30 degree in the first case, and in the second step what you are doing, you are rotating the object with an angle 40 degree. So you can say that you are rotating the object with an angle 70 degree, because whenever you are adding 30 degree plus 40 degree, it will give you 70 degree. But scaling is different. Two successive scaling operations, they are not additive, they are multiplicative. The composition of two scaling is multiplicative. Let S11 and S12 are matrices to be multiplied. So you can see that this is the first scaling that we are applying on an object, and this is the second scaling that we are applying on an object. So scaling, the resultant scaling is what? It is a kind of S1 into S3 0 0 0, S2 into S4 0 0 0 1. So this is the resultant matrix. Thank you.